So I'm Shu Yang from Material Science Engineering from Penn Engineering, and this is my collaborator Genevieve Diane from Drexel University just across the street. So what we want to show you today is the unique knittable passive probes for the in situ sweat collection and diagnosis. All right. So if you're a tennis player or you're a sports fan, you know Federer is well known for his all the bands, the headbands and the wristbands. The purpose for these bands is mainly to wipe out the sweat because they generate tons of the sweat during the games, right? So our interest is can we combine these bands and also take advantage of the sweat and develop some health probes and utilizing both of them having a winning product, and our winning product is a band which can change color depending on the sweat. So we will detect the sweat as a health probe. So why we're interested in this, the sweat detection and using the wearable technology? As you know, like wearable technology has been well developed and well interested in many, many different markets. And so for example, showing here, there's a lot of interest. So in the market, yeah, let me go to this way. In the market, there's many interest in the wearable technology, and particularly is a sensor. So this has a very steep growing path in terms of the sensor technology. And the benefit is you can do the detection, you can do the monitoring, you can do the data collection in the real time and also for prolonged time. So for example, I wear this, the Fitbit 24 hours. And on the other hand, the question is, are they comfortable? So my kids, my husband, they don't wear this 24 hours. I'm just a maniac, I like the data tracking. So the question is, how do we change this to other technologies? So the reason we like to wear this is because you can communicate, for example, using wireless communication, enable big data collection as well as relay, especially this is very useful in the remote places, in the rural places. So the question is, right now the Fitbit I watch, right, mainly focus on, for example, the health in the heart rate. They haven't really tapped into the area, for example, using the molecular, using the chemical, using the analyte. So our interest is can we actually develop some new technology in terms of the sensor. So here, what is the unmet need? So one of the we identified is the sweat. We think sweat offers a new opportunity for health diagnosis. So not only they can regulate our body temperature as a function of the temperature change, it also contains a lot of health, fitness, and data. So the question is why we haven't been developed, right, very well. So sweat tracking is typically considered less invasive, and possibly because as I mentioned, for the wearable technology, you want to have a long-term, relatively long-term period, and also for real-time diagnosis. So far, the sweat is very, very much underutilized for the health diagnosis. What we found is the only major product for the commercialization is to detect the cystic fibrosis in infants. So what are the problems? So the problem, as you know, during generating the sweat is also evaporating. So it's very, very difficult. The major problem is a collection. So current technology can only collect microliters of sweat. And in general, the average adult would generate 0.8 to 1.4 liter per hour, depending how active this person is. So as I mentioned, it's very, very difficult to harvest the sweat. And on the other hand, the major problem is the diagnosis. Because even you collect the sweat in the hospital and to use the conventional electrochemical or optical analysis equipment. So this requires using the administration and also laboratory instrumentation. And also the other question is sweat is multi-components.
Pardon me. Thank you.
Oh, okay.
Pardon
Sorry. All right. So the problem is the sweat is not just the temperature change, so there's many components, the chemical components inside the sweat. So whether you can generate multiple biomarkers. So this is one example. As I mentioned, it's only a commercial product. As you can see here, you have to strap the baby, and this baby is strapped on this disc. As you can imagine, it's not very comfortable. At the same time, to generate the sweat, they have to give you an electrode to stimulate the fingers or the arms to generate the sweat, only collecting 30 minutes. And as I mentioned, it's a very short time. So there's many possible errors in terms of the generation of the sweat. On the other hand, there's a new technology coming out, people trying to use, for example, turn the silicon technology into the wearable technology. So in this case, they can measure multiple parameters. But as you can imagine here, this is all fabricated by silicon technology. It's costly and it's multiple steps. At the same time, they still required conventional electrochemical instrument. And this one, when they do the experiment, they actually did 3,000 seconds. Who actually generates sweat in 3,000 seconds, in a sense, is using this as a data, right? So there's a lot of question in terms of the accuracy. So this is another example, again, from the Northwestern and L'Oreal. They use the epiderm electronics. So in this case, again, so based on the microelectronics, the industry, and also using the microfluid technology. So they introduce multi-parameters, again, using dye. So the key difference is instead of using the electrochemical equipment, they use dye. So you can generate the color. So based on the color, they can do detection. Then they use the iPhone to take the image, so you can transmit this information wirelessly. But the problem here is the sweat collection, similar to the previous problem, is this collection is microliter. And as I mentioned, the average adult will generate 0.8 to 1.4 liter. All right, so this is 6 orders of magnitude higher per hour. They can only collect, as you can imagine here, you put one sticker, you only can collect up to 1 hour. So there's a lot of limitation of this. So going back to look at our competitor, so we think there's many potentials. So because the real-time collection and full-body diagnosis, as well as for long-term purity, is still lacking in the market. And so we think we want to go to this area between the Penn and the Drexel collaboration. So I will turn to Jean-Vive.
So our concept is, of course, to try to integrate a system into a textile, but to make it pretty passive. There's a lot of research currently underway for biomedical textile devices. My lab has done several of those already, so I just wanted to show you some of the things that we've done. One is a smart fabric belly band and also a respiration monitor. So our goal is always to basically turn the garment into the device itself. And in order to do that, we want to have as few components as possible. So in this case, there's a very, very small little RFID chip in the middle up here that you can see on the focus of the belly band. So it still has a chip, but it's very small and fairly unobtrusive. So this is very, very important to us. And, you know, try to replace current equipment with things that are basically wearable on a daily basis. Do you want to change the slide on
next one? Just press
this one? Okay. Another product that we're working as a biomedical smart textile is an exoskin glove. In this case, it still has a lot of components. You can see at the wrist over there. I don't want to move the slide, but at the bottom of the wrist over here, there are some motors, but at the top of the glove, there are no electrical components. So we're always thinking about removing as much as the bulkiness as possible to turn these things into very close to the skin. So if you could see the other example at the bottom, it's really big. And so if you're thinking about human factors creating a textile device, this particular device, if you learn to pick up a cup with the one that's very bulky, that by the time that you remove that device, you would have to relearn to use something. So we have to think about all of these when we try to create textile device that can really help on the medical component. So we are design scientists who are looking to collaborate with scientists like Shu in order to create a new paradigm for textile devices. So in our lab, we use knitting as a form of fabrication. At the top, there's an explanation of what weaving is. It's creating a device. It's a machine that makes fabric, and it requires lots of threads. In order for us to rapidly prototype, we believe that we have to use a different system. So we use a knitting system. Do not think about your grandmother knitting a sweater. We use industrial knitting machines. But the reason that we love that particular mode of fabrication is because it's very similar to 3D printing. So knitting machine require just a few threads, and they can be changed very quickly, so we can do very quick experimentation and create a device very quickly, and it's a platform basically to create textile devices. So we think about knitting as a form of digital fabrication where we can do really similar things to 3D printing. We can rapidly prototype textile. We can do digital fabrication. We can model and simulate. We can actually make a prototype. Then we can scale up to pilot production if necessary.
Yeah, so I want to emphasize the instrument in Genevieve's labs is all industrial compatible. So anything we can knit on her machine, which means we can directly transfer to the industrial scale. So that's why we're interested in collaborating together, because our team has engineering materials, engineering capability, and then we can turn the engineering material into the design components. So our interest in this particular case, we want to develop a sweat responsive color changing band. So the single stage and the customizable manufacturing, and it's passive, super conformable, which is very, very important, because depending on the different person, so when they move at different locations, so you need to have this band to be exactly conformable to this particular person. So the knitting is providing this particular very unique capability compared to the weaving. So the knitting is really, really important. And of course, it's disposable, it's dynamically responsive, depending how you stretch, how you move. They can always conformable to your arm or your body components. And there's no use of the wire straps, as we saw in the previous, in the infant case, using the sweat detection. And it could be potential multi-parameter, and we can simultaneously do the collection and the detection. And more importantly, right now, is we use the sweat as a starting point. So our technology can be potentially in the future used as a platform to reach many other potential wireless the medical devices in combination with a wireless communication and the design of the fabric. So to combine this, going from the engineering material to knitting, we need to go from the fiber engineering from fiber, as we know, to knit, we need to have a yarn. So what we did is we started from the fiber electrospinning fibers, which is a well-established technique, but usually they're very non-woven and random. So we use this machine to actually twist them, just like we did usually twisting the wools, and we twist them into the yarns, and then we can produce these yarns not only in the micro scale, we actually generate into 20 meter long, so we can go to knit onto the machine. So this is our first prototype. The white one is our yarn, and then we can mix with different commercial yarn. And the other things, once we generate this flat one, the next question is we want to generate the band. The band is different. It's not flat. It's tubular. So that's why the knitting is very, very critical in this case, is using Genevieve's lab's knitting capability, so we can do single stage additive manufacturing. In this case, it's seamless. We don't need to have anything to stitch them together. So they save the material, as well as very sustainable. And as we mentioned, this band is very dynamic. So what we did is to enhance the capability of the knitting, we engineered the yarn. So from single yarn, we go to the core sheath yarn. So that means we can combine the commercial one together with our engineering one. So this is one example. It's a red color yarn, and we tested the color. So this is the single yarn, just our engineering yarn. As you can see, they can change color from red to transparent and go back to light red. And depending on the analyte, we can have different color intensity. And then we use the engineering yarn as the core sheath. The core is a commercial one, it's a green one. So when you wrap around with red, when you don't see the green, but however, when you change the analyte, you can actually make the outside sheath become transparent. Then we can display the green one, the green yarn inside. And we also have a first prototype that the knitting is the tubular structures, which is a wristband. So we're very excited about this. And going back to the timeline, so we are in the first stage. Around this stage, we demonstrate a proof of concept. And the next question is how do we integrate into a real prototype and go to the next stage. So one of the questions is how do we interface when we choose the analysis? We need to choose the analyte dye pair to enhance the colorimetric readout. And then we want to interface with a smartphone and enable a multicolor analyte detection. And as I mentioned earlier, so this is just the first demonstration for the sweat. So there's many possible medical applications. We can use our wearable sensors. And so next stage will also, when we design all these wearable sensors, we'll take into the mind is the clinical trial in terms of where do we mount this, and male, female, young and old, as well as the duration of the collection time. And so at the end, I want to introduce our team. So as I already mentioned, so we have engineering students and postdocs working together. We also work with a design scientist across the street. We have a consultant, Jianbo Xi from Penn Engineering as well, who's well-known in the vision recognition and the human interaction. And he's also a member of our robotics or GRASP lab. And what we're looking for is a medical collaborator, so we can narrow down the application at the first stage.